Morning, good afternoon, and good evening, everyone. So today we're going to be talking about double integrals in polar coordinates. So recently we've been talking about double integrals, bottom line, and we did that with rectangles. And then we wanted to do something more general, so we did that over general regions. I did in the homework, right? We did videos on the homework on general regions, and right now we're doing it in polar coordinates. So this is just, again, another technique or another way to think about how to apply double integrals. And so let's hop right into it. So suppose we want to evaluate some double integral where this region R is a circular disk, right? So let's say we have this double integral. However, R is a circular disk. Then how would we solve that? The region is a circle, and let's say it's centered at the origin. And so in this case, the description of R in terms of rectangular coordinates is rather complicated. However, R is readily described using polar coordinates. So that's where polar coordinates come into play when you have something circular, right? But more in general, if R is some region that is more easily described using polar coordinates, it is often advantageous to evaluate the double integral by first converting it to polar coordinates. So we're going to convert, right? That's the idea. So again, it's just another technique when we have something along the lines of that. So let's do a brief review of what this is. So what are polar coordinates? Simply put. So it was discussed in section 10.3. The concept of polar coordinates were newly introduced in section 10.3. And so let me show a quick figure of how this looks like when we apply it in 2D. So let's go to the 2D XY plane. Oops, I have the figure, but okay, there. Cool. Okay, so what are these? The polar coordinates are theta of some point are related to the rectangular coordinates xy, right? By these particular equations, we have r squared is x squared y squared, as this is our radius. And then we also say that x is r cosine theta and y is, so this is a pre-calculus thing. Y is r sine theta. We multiply radius to have some angle to get that y value, right? How else can we say that this is true? Well, let's go back. What is cosine theta if we have this right triangle? Cosine theta is the adjacent side over the hypotenuse side, right? And so I could just multiply both sides by r. And there you have it. And that's the same for y equals r sine theta. We're getting the opposite over its hypotenuse, and then we're multiplying r to both sides to get that. So that was the idea or the algebraic explanation behind it. And so in general, equations of circles centered at the origin are particularly simple in polar coordinates, Why is that? Because the unit circle always has an equation of r equals 1, right? Because the radius of a unit circle is always 1. And so the region enclosed by this circle is shown in figure. Let me just show the figures before I yap too much. Oops, I did not include the. Still here. Okay. Yes, so as I was saying, this here is the unit circle. That's the unit circle. I know I didn't trace the green circumference very well. So that's figure 2A. Now, figure 2B illustrates another region that is also conveniently described in polar coordinates. Why is that? Because my r theta, all of my points r theta, r is in between 1 and 2. How do I know r is in between 1 and 2? These are both circles, equation of circles. This has a radius 1, and this has a radius 2. Whoops, my bad. I almost said 2. I almost said 4, I mean. 2 squared is 4. And so my radius is somewhere in between those two things, which that's one of the restrictions or conditions when I'm doing my set, right? And similarly, theta is from 0 to pi. Now, how do we know that? 0, we move here. This is a full, or not really a full, a half rotation. So that's pi. If I had a full rotation, that would have been, full rotation would have been 2 pi. But in this case, it's just pi because it's just half a rotation. Or in other words, 180 degrees. Right? So these are also some things that we can conveniently describe with polar coordinates. Okay, now let's talk about applying double integrals to polar coordinates. Or wait, can I? Oh, before I do that, let me do some exercises here. Let me show these. Okay, I hope it's visible. Yes. So every time I complete something that I think is going to be related to the homework, I just go ahead and do it, or I attack the problems immediately. So here we're being asked to sketch the region in the plane consisting of points whose polar coordinates satisfy the given conditions. It says here my r is greater than or equal to 3. Now, what does that mean? It means I have a radius equal to 3. So in this case, I think all of these work. And it should be a line, not a dashed line like these two, because it says equal. And now it says that it's greater. So I go outside. And my theta is from 0 to pi. So it's this one, I think. If not, then it's something else. Oh, it should be good though. Yes, got it. Okay. Next, sketch the region in the plane consisting of points whose polar coordinates satisfy the given conditions. So my r is from 0 to 5, or it's in between 0 and 5. Here in this case, 0 and 5 is, both of these work. Oh, now these two are gone because they don't have a these have a radius of 2. So I'm left to pick from these two. And I'm going to use my other information. It says that my theta is from negative pi half to pi half. So negative pi half is actually here. Oh, that's tricky because of the rotation. But notice here, it starts from the negative. So it starts from here. And I'm assuming this is counterclockwise because positive angles are always counterclockwise. So I would say it's this one. If not, it's probably this one. So yeah, this is my answer. Because this starts from negative pi half going all the way to pi half. And also has a radius of 0 to 5. Okay, got it. So there's also the pressure of trying to get it correct while doing this video. No worries, it's my first time going through these. Okay, so same idea. We sketch the region in the plane consisting of points whose polar coordinates satisfy the given conditions. And so we have my radius being from 1 to 3. Now this one's tricky because these are oh. Oh, actually, this one's gone because there's a radius from 1 to 3, right? And it says it's less than my radius is in between 1 and 3, including 1. So 1 with dashed lines are gone. So I have to pick from these two. And then we use the other information, which was from 3 pi fourth to 7 pi fourth. So starting from 3 pi fourth, where does that start? 3 pi fourth is how many in degrees? Let me just double check. So there's a formula for doing that, and it usually works. So I do this, take these out, and then I calculate that thing. This becomes 1, this becomes 45. So it's 135 degrees in the positive thingy. So somewhere 135 degrees would be here-ish. This is 180, flat is 180. And then it says it goes all the way to 7 pi fourth. Oh, I should have done it again. So 7 pi fourth, if I were to do the conversion from degrees, from radians to degrees again. 45 on. So here we get 300. Whoa, 315. Mm-hmm. Yeah, 315 degrees. So it goes from 135 to 315. So here to here. So I'd say this is the answer. Not super sure. I think it should be this one. Also watch it in case. Let's see. How many tries do we have? Like 5. Okay. I'd say that's the answer. Because again, we're thinking of it in a counterclockwise manner. Okay, we got it. Again, sketch the region in the plane consisting of points whose polar coordinates satisfy the given conditions. Okay, now it looks like we have weird boxes. So my r here is greater than or equal to 0. What does that mean? My r or my radius is either 0 or greater than, but it can't be, there's no such thing as a negative radius. Now, I can't really tell that because there is no there is no circle anywhere. So that's cool. Okay, what else? It just means that it goes beyond, I think. And I don't know. Okay, here we start from pi half. Pi half is here, going all the way to 2 pi. So I would say going all the way to here for a full rotation. This one doesn't do that. This one definitely doesn't do that. This one doesn't do that. So I would say it's this one, right? It covers that angle. The angle wise, it's covered from pi half to 2 pi. My R, however, I think it covers, right? Because I have an infinite radius, basically. So these ones are all covered. Let me try. Not super confident, but okay. Nice, got it. Okay, now we have find a Cartesian equation for the curve. So this one, okay, let me go back to my thing here. Let me just flop to the homework. So here we're being asked to find Cartesian equation of curve, of some curve actually. And what is that? So r squared is equal to 14. And when we say Cartesian equation, what does that mean? Did we talk about that already? No, because I already went straight to those integrals. Anyway, I'll just load the video. Mhm. So it's okay, apparently it's a circle. So basically it's just x squared plus y squared equals 14. It's basically a circle. We'll see. Yes. Okay. Yeah, I got it. Next, let's do another one. So another find the Cartesian equation thing. So this one, we're given r is equal to 5 cosine theta. So what would be a Cartesian equation of that based on what we know? I mean, it's really just mm-hmm. What might this be? Okay, let's think about it for a bit here. R is equal to 5 cosine theta. Well, the idea is to get maybe to r squared again, right? So why not let's do that, similar to this thing. And then we follow that formula. So we have r squared is equal to 25 cosine squared, right? And then we can plug that one in to my x squared y squared. Oh, I almost forgot. Oops. When I do an r squared, I basically multiply this by an r. Close error. Super close. Right? And then from there, now I can just say my x squared plus y squared is equal to 5r cosine theta, which is just 5x, right? X is equal to r cosine theta. That's the Cartesian, we call that a Cartesian equivalent of the polar coordinate, right? And then from there, let's just rearrange the equations. We get something like x squared minus 5x plus y squared equals 0. And then now here's something I would do, but we just complete the square, right? So that's going to give me x minus 5 half squared plus y squared equals 25 over 4. And so it's basically a circle with some center 5 halves 0 and a radius of 5 over 2. So that's the idea behind that. So it's still a circle, just an interesting one. Yeah, so it's really, really cool how we could like describe them like this. I've never seen it described in a way like this, not even in my Calculus 2 class. So this one's pretty new to me as well. Okay, let me just type that in. Circle, and let's see. Okay, still loading. Nice. Okay, another one. Let's keep it rolling. Oops, I did not mean to do that. Okay, now I'm. Sometimes this OneNote is bugging me. Okay, so we find Cartesian equation of curve again. And here we have theta is equal to pi over 6. Now, what is this? So here really, we want to be able to try to derive something out of our previous calculus knowledge here, right? So what information can we use to find y and x in terms of theta? So maybe something helpful to use. So here I'm just jotting down ideas. But something helpful would be tan theta is y over x, right? Because usually when we have a typical right triangle with some theta, some y and some x and some hypotenuse. And so that's some helpful relationship to describe. So that's a trigonometry topic. And so, okay, then why not let's just do this, right? And then from there, let's just rearrange the equation to solve for y. Or we could evaluate it actually. So if we evaluate this thing, this is just 1 over square root 3. Look at the trig table to do that. And then I evaluate it. So here I get y is equal to this thing times x. So what do we notice? There's actually a line. The thing's a line. See if we got nice. Okay, more sketching stuff. And then now we get into the integrals, which I'll do. Yeah, I'll do that later. Let's just finish the polar equations part. Okay. Yeah, I think this was the last one-ish. So now we're gonna do it in reverse. So instead of us being given the polar equation, now we're given the Cartesian curve or Cartesian equation. So here it's basically reversed. Okay. And then we have this assumption that my theta is in between 0 and 2 pi. Okay. And so here's our equation. X squared y squared equals 6y. So here we can immediately see, based on our previous examples, you can see that r squared is 6y, right? You can see that. What else do we notice? Well, my x and y are basically r cosine, and my y is r sine, right? Mm-hmm. And so based on what we've derived here, y is r sine theta. So we can say that r squared is equal to 6r sine theta. We can take out an r, so 6 sine theta. And that's the answer. So we just used this idea, plugged it in here, then got that one. And that's it. Sine theta. Let me just hit submit and see what happens. Nice. Go ahead. Okay, number nine. Let's sketch the. Okay, back to sketching curves here. It's back to sketching curves. So this is something I'm just gonna do it like right here. So if we're given some r equals 6 times 1 plus cosine theta, that means my radius is that thing. Mm, okay. Looks like a heart. Mm-hmm. Okay, I can't really tell 'cause I'm not. Yeah, I think I have to go back to my writing thing and then just do this. So it wants me to sort of sketch it, but I think in reality, what it wants me to do is convert it to a polar equation. Yeah, I think that's what it wants me to do. Let me just watch the video and see. Should be something like that though. Or I just plug in. That's pretty cool. That one's smart. It's really just okay. So what he did was he plugged in. Hmm. Mm-hmm. Whoa. This is more tricky than I thought it was. Mm-hmm. It is definitely a hard shape. 0 to pi half. Oh, okay, never mind. I got it. Kind of. We'll see. So the idea here is we want to sort of plug it in. So we want to make values for r and theta, right? So my theta starts from 0. So here we want to keep track of the rotation as much as possible. So the way we can do this is the typical of each coordinate. So that would be 0. So if you were to like look at it from this perspective, 0 starts us here, and then we go here, rotate to there, that's pi half. And then we rotate to here, that's pi. So it's really more on rotation that we're focusing here. We go here, that's 3 pi fourth, I believe. 3 pi is 270. What's that in radians? I have no idea what that is in radians. Like 270-ish. Okay, 2/3. Let's do this one's 3. Okay, so it's 3 pi over 2. Then lastly, the full rotation is 2 pi. Okay, so we want to... Uh-oh. Where did we get that part? Oh, yeah, I forgot about the pi. What the? Pi, the 180. So here's pi. And then 3 pi half is that one. And then 2 pi, which is the full rotation here. Yeah, so we basically want to consider all of these things as we're rotating. And then the full rotation is back to 2 pi. And so what are the R values if we were to plug in 0? Cosine of 0 is, well, 1. 1 plus 1 is 2. 6 times 2 is 12. So radius here is 12. And then pi half, well, here, this is pi half. Where in the world is that? Cosine pi half is 0, I believe. Yeah, so 1 plus 0 is 1 times 6, 6. Pi, cosine pi is -1. So we have 1 minus 1 is 0. This thing is 0. Then we have 3 pi over 2. And so this one is 3 pi half. What's that? Oh, here. That's just 0, right? Yeah. Pretty sure that's just 0. 1 plus 0 times 6. And I think this is back to 12, if I'm not mistaken. So it's 12, 6, 0, 6, 12. So if we were to sketch that whole thing, well, we would get something like this. So 12, 0. I start at 12 as my radius. So here I'm assuming I'm at the origin, right? And I haven't rotated yet. Now at pi half, when I rotate here, I'm going to get the 6. So 6. So I might do something like this, right? Because I'm rotating. Now, I still don't know how to define this curve mathematically. Because I thought, why not it just be a straight line? Well, because it's rotating. But how steep is that curvature when we're rotating? So that's something I haven't figured out yet. And then we go to 0 at pi. So at pi, go here, then we go to 0. So this is where at pi. And then from there, 3 pi over 2. So from here, from this point, we go 6 again. And then from there, we go back to 12 when we rotate here. So it really is that sideways heart that we're looking at, right? Okay, let me just quickly go there. And I thought it was going to be some simple like thing where we can just, anyways. And so same idea. We just want to do the same thing, plug in, see what we get. So we get the some radius once we rotate at some angle. That's the idea of polar coordinates. Okay, so let's do that again. I think it was number 10, right? So again, we sketch curve. We're given some function of r of theta. So you have 4 cosine 2 theta here. And so again, let's do the point plotting by default here. This is theta. So here, let's say this was 0. So the typical ones, pi half, pi, 3 pi half, 2 pi. So when my cosine is 0, well, that's just 1. So this is 4. This is pi half, this is pi. Cosine pi is 0, I think. Or negative 1. What was negative 1? Times 4, so that's negative 4. Pi, on the other hand, is... Oh, that's 2 pi. That's a full rotation. This is 4 again. 3 pi over 2, that's... I just cancel it. So I get cosine 3 pi. Ooh, what is that? Negative 1 times 4 is negative 4. 2 pi, here's 4 pi. Cosine 4 pi is, I think, just 1 because we just rotated twice times 4. So again, how would that look like if I were to draw it in my xy plane? Well, my 4 here, oh, probably here, starts at 0. And then at pi half, I'm at negative 4. 4 is here. 4. Okay, they're all 4s. There we go. So 4, 0, I'm here. At pi half, I'm here. Or I'm at negative 4, actually. Oh, wait. At pi half, I'm at negative 4. What in the world does that mean? What? Wait a minute. Wait, I just realized this. What does it mean to have a negative radius? Yeah, I just realized this. What does it mean to have a negative radius? Okay, let me go ahead and rewatch the video because I don't know. Hmm. Okay, wait. I can't. Okay. It oscillates between. Mhm. Wait. I'm trying to like copy, quote unquote, copy the video. Okay. This is 0. Negative 4 when it goes down. Goes up to pi, I think. So 4 again if it's pi. Go down again if it's 3. Go up again if it's a full rotation. So this is 2 pi, right? Oops. Oh, what am I doing? Can't see the video. Okay, where's my pi again? I totally forgot. Here, here's my pi. And the other ones are, this one's 0, this one's pi half, 3 pi half. So everything that's half is under here. And then we want to divide it by some divisions. So what is this one intersects this thing here? Well, let's just pi half plus 0 divided by 2. So this is just pi fourth, right? When it intersects this thing, that's pi fourth. How do we know we just make this thing 0? Cosine. Oops. We make, what am I saying? That thing here is pi fourth. So, oh, when's my R 0? What? Oh. Yeah, so we take note of this, right? So at 0, when my theta or my angle is 0, when I'm here, I'm at 4, right? And then once I approach pi over 4, which is basically half of this thing, right? This thing is pi over 4 because this is pi half. Well, then here what's happening is I'm rotating from here to 0, right? Now I'm here at 0 again. And then once I'm at 0, here I go down to -4 at pi half. Now what does that mean? What the? Wait a minute. See, it's this thing where like, oh shoot, I got it. Now I don't get it again. Pi over 8, and then from here, his example is weird. Oh, that's what it means. Whoa. Comes out of the opposite side. So it comes out from, so when we're from here, we come out here, right? This is pi half. I go to -4. God, this is so confusing. What the? Okay. So now I'm here, right? Because I went down -4 pi half. And then I go back up to pi. Or I go back to the zero here. What in the world? So I basically keep going back to zero. And then now I go back to pi. So what does pi tell me? I'm at 4 now for some reason. God, this is. I think I just go up here pretty much. Yeah, and then I go down again, back to zero. Then I go down here, that's 3 pi over 2. I go here. And then I go back to zero. Then I go all the way to 2 pi, going all the way back to 4. That's pretty annoying. See if you got that one. Okay, yeah, we got that one. Yeah, that one's really, really, really tricky. Anyway, so I'm gonna stop the video for here right now. And I hope you guys enjoyed and learned a lot. And I'll see you all in the next video.